Alright, welcome to today's lesson. We're continuing on with where we left off with standing waves last class. First, what we're looking here is a PhET simulation. And we've got a few different things we can show you here. One, I would like to show you one quick thing about depending on whether the end of the string is fixed or loose or not held on at all. We've only talked about reflecting waves off of a solid barrier, off a fixed end. And what you do see is what we've seen before. Actually, let's turn the dampening down so there's no absorption of the energy and the wave doesn't die down. Try again. And there you see that the wave reflects negatively. Now if we reset it and we change it from a fixed end where it's held in place to a loose end where it's free to move up and down. We didn't get a chance to get to this before we had to go to e-learning. But when you have a loose end that's still attached to a pole but it's free to move, you'll see something different. And so what you see there is when the wave reflects off a loose end, it comes back positive, but when it comes and hits the fixed end, as it comes down here, it reflects negatively. So again, a loose end, I keep hitting the wrong button there, a loose end reflects positively, comes back on the same side it had arrived on, but a fixed end right here where it's held in place comes in positive but then comes back on the negative side. So fixed ends reflect negatively, loose ends reflect positively. And then finally, what happens if we have no end, if there's strings not being held at all, and if you just send a wave down there, well, you get no reflection at all, it just leaves. So we wanted to make sure we had just covered that. That was a minor point we were going to get to. Now, as we talk about standing waves, what we're going to be taking a look at here, we've taken a look at this, and as waves come in, we can have it go, as the animation is just kind of slow. As the waves come in, we say those waves are incident. They are coming in towards, and we have a barrier here that is fixed, so we expect a negative reflection. And that reflected wave shown in blue. And so as the blue wave comes back, remember that waves do pass through each other. We call that interference. And we can pause this at certain moments. For example, right here, what we have here is a crest interfering with a trough, and those two will cancel each other out. Remember, that's called destructive interference. You let it go a little bit further, and there you have the same parts of both waves. Two troughs add up to make a larger trough. Two crests add up to be a larger crest, and that is constructive interference. And when you have a standing wave, it happens at certain conditions where the wavelength is a certain percentage of the length of the string that you have, and if you vibrate at a certain frequency to create that wavelength, you can get a standing wave, which if you take a look at the black lines here as we resume it again, well, that wave looks like it's just vibrating up and down. You don't see in the actual string itself the sideways motion of the waves that are coming in incident and reflecting back negatively. We can go and pause that again for a second. So if we take a look at this, these are the different standing wave patterns that you have with two fixed ends. Now, right here, this is the length of the string. And at either end we have the fixed points, which are called nodes. And I do want to say that the rules are a little bit different. If you have something that is loose at the end, we'll cover that a different day, but right now we're just talking about strings that are fixed at both ends. So at the lowest possible frequency where you can set up a standing wave, you have this wave. As you multiply your very first frequency there to set up the first wave, you can get multiples of that fundamental wave. If we take a look here, we do need to point out that for that very first wave, this right here, that's not a full wave. Remember, a full wave has a crest and a trough. And so hopefully what you can see here, we did discuss this last class. As you have a crest and a trough, that is a full wave. So if you only have the crest side, well, that would only be half a wave. And so we have this formula right here that the wavelength is twice the length of the string. In other words, this is the length of the string from edge to edge, Well, that is just one half of a wave. You actually have to go twice the length of the string in order to get an entire wavelength, which is what you see here. So this is twice the length of the string to get a full wavelength. Now that's at the lowest frequency. Now what happens if you start doubling, tripling, quadrupling the frequencies? We have a quick little video there. And so what you see here is, this is the very first harmonic. This is the very lowest frequency that you can set up a standing wave. And so you see how it's just going up and down, up and down. Now remember that these points that move the most are called antinodes, which are the opposite of the points that don't move, which are called the nodes at either end. Now, in order to set up the next wave pattern, we'll come along here in just a second. And what you see here is you have an antinode here and an antinode here, and at this very moment you see an entire wave. So at the second harmonic we have a one full wavelength, and so at the second harmonic the length of the string, in this case the spring, is going to equal the exact wavelength of the wave. As we continue, you can see that there's more waves that can be set up, but when they show these waves where they have a top and a bottom in the picture, let's go back again very quickly. When you see the top and the bottom, that's showing the extremes that the wave can travel. So it's actually traveling up and down here at the antinodes. And I can label those as you have a node and a node, and the antinode is where it moves the most. Here you've got 3 nodes where they do not move, and do not move, but then you've got 2 antinodes where the movement is the greatest. So again, when you see it drawn like this, sometimes it's with a dotted line to show where it is a moment later, but where you see that go up and go down, that's the point of most motion. And that's what's being shown right here as this wave moves up and down. So here is 3, 1 antinode, 2 antinodes, 3 antinodes. But what you want to notice is, for as far as full wavelengths go, we have, if you're going up and then down and then up again, right there from here to here, that is one full wavelength. And then here you just have the crest with no trough, so that is another half wavelength. So we have 1.5 wavelengths. You could also say that as 3/2 of a wavelength. So as you increase the frequency, you will find more antinodes as the wave gets shorter, and you will go in multiples of halves. So here we've got the first harmonic, which has 1 antinode. The second harmonic has 2 antinodes, and that's actually a pretty easy thing to count. The N number right here is the number which harmonic you were on, and it happens to match how many antinodes you're going to have. So if you were with the 4th harmonic, you would expect to see 1, 2, 3, 4 antinodes as you set that up. And again, when you take a look at this, at the 4th harmonic with 4 antinodes, you've got 2 complete waves. In other words, you have 4 halves. Each harmonic is going to be responsible for basically half of a wavelength on the string. When you have 3 harmonics, you should see you've got 1/2, 2/2, 3/2. So 3.5 wavelengths can fit onto the length of the string, or if you rearrange that, you can say 1 wavelength. 1 wavelength is, if you divide this into thirds, 1/3, 2/3, 3/3. 1 wavelength is 1/2 of the length of the string. So here we can say at harmonic number 3, the wavelength of harmonic number 3, we have 2/3 the length of the string is going to be the length of the actual wave at that frequency. Now, you have done problems with this. As a matter of fact, last time we were in class, we had you figure out how to find the wavelength, how to calculate the frequency, and then on your own you were able to figure out the speed of the wave using the basic wave speed formula. The velocity of the wave speed, equals the frequency multiplied by the wavelength. Now, one thing we want to point out right here, the speed of the wave does not change if the medium doesn't change. So just because you shake the spring or the string faster, more often, with a higher frequency, that does not change the speed of the wave that moves. So the speed of the wave is going to be constant as you shake the spring or the string at different frequencies. But if the frequency goes up to equal the same velocity, well, the wavelength is going to have to go down. It's going to have to get smaller. So as you wiggle the string at higher frequencies, the wavelength is going to decrease. Or conversely, if you shake the string at lower frequencies, as the wave travels, it's going to get further before the next shake comes along, so the wavelength is going to increase. To put some numbers to it, if you calculate or measure the wave speed at 200 meters per second, well, that could be 20 meters happening at 10 times per second. Remember, hertz is a wave per second. So 20 times 10 gives you 200. But if you shake it more often, you go from 20. Oh, I just realized I've got my wavelength and my frequencies reversed for here. But the math still stands. If you go from 20 meters, a large wavelength, or medium-sized wavelength, to a larger wavelength, in order to compensate, you go from 10 hertz, 10 waves per second, down to 4 waves per second, 4 hertz, and you still get a total wave speed of 200 meters per second. The wave speed does not change, even though the frequency and the wavelength are changing to compensate. As one gets larger, the other gets smaller, and vice versa. They are the inverse relationship of each other. We can also see this. We've got a video here that kind of demonstrates here. Now as you listen, I want you to take a look at the bottom string here. Now, this is going to be the highest notes that you hear, and when you can hear that string being played, you should be able to see what happens to the distance between the waves when you hit the higher frequencies and the lower frequencies. So let's take a listen. So if you are watching that, you can hear that high note. When the note gets lower, the waves get further apart, and when the note is higher, let's see if we can. We'll just do this. So right back there, what we just saw was that when he was playing the high note, you saw that the waves were pretty close together, and when he played the lower notes, the waves got further apart. And so this happens in any musical instrument that has a string. You'll notice the same thing. As you play a higher note, as the frequency goes up, you have a higher pitch, the waves will get shorter, and as you lower the pitch, you play a lower note, the waves will spread apart. So what we're going to take a look at next is just one other example. So here we've got the exact same length string, but we're playing the different harmonics. So this would be the first harmonic, also called the fundamental frequency, and you see it only has one antinode. Now the exact same length of the string, if you vibrate it twice as fast, and if you take a look, you should be able to see that this is moving half as fast, or you could say this is moving twice as fast, twice as often. I should distinguish between speed and frequency. So this is vibrating twice as often. And so as the frequency went up, the wavelength, the distance between from crest to crest, has actually decreased. Now here you see 1, 2, 3 antinodes, so that'd be the third harmonic, and you see how it's shaking 3 times as often as the first harmonic. And finally here you've got the fourth harmonic, so you've got 1, 2, 3, 4 wavelengths, and you see it's vibrating 4 times as quickly, 4 times as often as the first harmonic, the fundamental frequency. So now we're going to take a look at what you're going to be doing for your assignment. So we've got a link to FET on the website, but if you want to go ahead and type in FET waves on a string, this will bring it up to you. And we will want to have it, this is how it comes when you first load it up. We're going to pause it for a second. We're going to set it to an oscillation. That means it's going to vibrate up and down over and over again. It's going to send a wave in. It's going to reflect back out. We're going to keep it on fixed. And if you hit play, we can see that some waves are already being set up. Now, what the goal we'd like you to do here is to be able to actually use the information that we have here in order to calculate what the fundamental frequency is going to be. Once you have the fundamental frequency, the first harmonic, what's the frequency of the very first standing wave? And again, that would be a wave that looks like this. So we're going to be looking for this first frequency. And then once we know that, we're going to go ahead and take a look at the relationships to find how would you find the second frequency, second harmonic, the third harmonic. And basically what it boils down to is that when you have the different harmonics, where did I have that? Here we go. If you want to find the second harmonic, the third harmonic, the fourth harmonic, it's really, really simple. All you have to do is take the very first harmonic frequency and go ahead and multiply that by whichever harmonic you have. So the second harmonic would be twice the frequency of the first. The third harmonic would be 3 times the frequency. So if you, as an example, were shaking this up and down twice a second, the second harmonic would be 4 times a second, or 4 hertz. The third harmonic would be 6 times a second, which is 3 times your very first. And then finally, the fourth harmonic would be 4 times your fundamental frequency, or 4 times the original 2 hertz, which would give you 8 hertz. So moving back to what we're having you do for the assignment, one thing you do want to change is down here, change the damping to none. The damping again reduces the energy as the wave travels, and so it makes the wave a little bit lower amplitude as it goes along. It makes it a little bit more difficult to see what's going on. And I'm going to keep my attention at high. For your assignment, you can set it to low, medium, or low tension, but since I am doing high tension, I'm saying you can't use my results. You have to pick either medium or low. So again, your settings, basic settings, but change your damping down to none and choose a different tension other than the default high setting. So as you continue to hit play, in order to figure this out, I'll do an example for you. What we'd like to do is actually see how long this wave is. And when it's coming back reflecting, it's kind of hard to tell because the waves are overlapping. So actually what we're going to do is we're going to hit no end. And so you can pause this at any moment. And then over here you've got your tools. We're going to use the rulers. So if I want to know how long a wave is, you just go ahead and measure. For example, right here I see that starting at 0, I measure all the way over here. Now something to be very careful of, you notice there are not 10 lines between each number, which would have made it 0.1 centimeters. There's only 5 lines, so each one of these lines is worth 0.2. So this would be 0.2, 0.4, 0.6, 0.8, and then that would be 2.0. So here we've got 1, 2, 3, 4 centimeters, and it looks like one line passes. So that's about 4.2 centimeters is my wavelength. Now, if I know my wavelength is 4.2 centimeters, and my frequency right down here shows me that that's 1.5. Well, we can go back to our original wave speed equation, which is right here. Wave speed equals frequency times wavelength. So if I go ahead and plug those numbers in, 4.2 centimeters multiplied by a frequency of 1.5, well, I get a wave speed of about 6.3 meters per second. So going back, once you have your wavelength and you know your frequency, you can find your wave speed. And once we know our wave speed, we're going to go ahead and set up the standing wave by figuring out what frequencies it should have. Now, how are we going to do that? Again, we think about what do we know in standing waves. We know that in the first standing wave, that the wave is actually twice as long as the string. So the wavelength is twice as long as the string. So if you happen to know the length of the string, you can double that, and that would give you twice the length of the string, would give you the wavelength. So going back to our video, we are going to again click back on fixed end. We're going to restart this, and let's see how long this is. So you can measure from here to here. That's 7.2, 7.4. I move that a little bit so I can see the lines. Maybe I'll measure from the beginning of the green to the end of the green. Alright, it looks like it's a little bit difficult to see the exact number because it's being covered up slightly. But it looks like 7.2, 7.4, somewhere between 7.4 and 7.6. We can estimate about 7.5. That'll probably do a pretty decent job. So now I've got the length of my string, and I happen to know the speed of the wave. Well, if you know those two items, you can go ahead and find the frequency, again, using your wave speed formula. Going back here. Using your wave speed formula, if you've already calculated the speed of the wave and you've calculated the length of the wave for the fundamental, again, thinking that the wavelength of the fundamental is twice the length of the string, well, then you should be able to hopefully fairly easily rearrange this equation to solve for the frequency, and that would be the frequency of the very first fundamental wave. In other words, that would be harmonic number 1. Now, using what you've learned, harmonic number 2, harmonic number 3, those would just be the multipliers. Harmonic number 2 would be twice the frequency. Harmonic number 3 would be 3 times the frequency. Now, when I did my math, what I came up with, again, you have to use either medium or low tension, so that will change your wave speed. So we have some different numbers here. But when I did mine, I came out with a frequency of about 0.42, so I'm going to set that to 0.42 hertz. Now, I'm going to tell you right now, based on what I've practiced, it doesn't come out as a wave that's exactly perfect, but you should be able to definitely see the standing wave. So we're going to go ahead, hit play, and once you have the reflection coming back, what we see here is, there you go, there's your fundamental standing wave. Now what you'll notice, it gets very, very high. That's because we don't have any damping turned on. None of the wave energy is leaving. So as you add more energy, it's going to get a taller and taller amplitude. In real life, you'd hear noises, you'd have some of the stretching creating heat, so some of the energy would leave to a point. But this is a situation that you've probably heard of where we call it resonance, where if you continue to put energy in at just the right moment to match the frequency to make the standing wave, the waves will get larger and larger. So there's your standing wave. Now we said that the second harmonic would just be twice the frequency. Well, twice the frequency of 0.42 would be 0.84. So let's get this down as exact as we can. We're going to hit restart to smooth things out. Go ahead and hit play. And again, it's not going to be exact, but what you do see is a pretty good second harmonic wave where you've got one antinode and two antinodes. And then if we wanted to go ahead and show the third, well, 3 times your original frequency, 3 times 0.42, if I do that in my head, see, that'd be 12, and so I think 1.26, if I did it right in my head, we'll go ahead and start that, and hopefully if I did things right, there we go. So you've got a good third harmonic with 1, 2, 3 antinodes. Again, it's not going to be perfect. Things are going to move around just a little bit here, but that shows you pretty well what's going on. So that's your assignment. Now we've posted that assignment. I'm going to modify it a little bit here after I'm done with the video. But if you go to our home page well, I guess you've already found part of this because you're here. Your e-learning assignment for this day, I'm going to have to get to it because I actually haven't published it for you yet. I was making sure I had ironed out all the kinks. Here we go. So you should see your instructions for the assignment. Got the link to the FET simulation. But again, don't use the high tension setting. Go ahead and use medium or low tension. Figure out the speed of the wave. Once you know the speed of the wave and you measure the length of the string, go ahead and find the first harmonic. Once you know the first harmonic, then go ahead and calculate the frequencies for all of the first three. You've already done harmonic number 1, find harmonic frequency number 2, harmonic frequency number 3. Now, when you've gotten those standing waves to come out, pause the pattern and do a screen capture. And if you're not sure how to do a screen capture, the last thing I'll show you here is this. On your Chromebook, you should have these buttons. If you hit Control Alt, and right here, right above the 6, if you hold these two and then press that button, you should be able to do a screen capture. And you, in your Google Doc that you create for me, you can go ahead and paste the pictures into your Google Doc to show the patterns that you have set, and in those patterns you'll also be able to see what the frequencies are and what you had your tension set to, so you'll be able to see all of that. Heading back to our page. So again, create a Google Doc explaining what you did, showing your calculations, and showing the pictures of the wave patterns that you create. Now, as always, if you have questions, I need you to go ahead and make sure that you email me. Go ahead, include a phone number, so if it's much easier to go ahead and explain it so we can have a conversation, we'll go ahead and do that. I wish you good luck, and please do not hesitate to contact me.